Hi, this is Justin Aquilante, ESA Sales Director, here today with Seth Simpson, Regional Sales Manager for Bender. Seth, welcome.
Thanks for having me, Justin. I appreciate it.
Seth, what risks do you see associated with battery energy storage systems?
Yeah, Justin, that's a great question. There are very common risks that are associated with battery energy storage systems. The most common that I would say the general public is aware of is fires around these. Of course, you see fires when you have thermal runaway on these devices. That gets the media's attention for sure. You see those risks. The unseen risks that you have are really your personnel protection. So anytime there are people around an energized installation, that is, of course, an associated risk. But the biggest one I think that is often overlooked is actually the loss of power or your battery energy storage system not operating as though it was intended to. So for example, we use battery energy storage systems for critical power, critical loads when you really need it. If that power is not available and you are expecting it to be available, that is a significant risk that is often unseen within the industry.
Seth, there are two types of electrical grounding that are currently being used in battery energy storage systems, ungrounded and grounded. Can you explain these two systems?
Yes, absolutely. And it's very important to understand the difference between these two systems because the safety that goes along with it will be dictated by what system type that the battery energy storage system is operating on. So the grounded system, again, we are very familiar with this in the United States. This is what is in our household, a solidly grounded system. You have a hot, a neutral, and a ground in any standard outlet. In a battery energy storage system, a grounded system means that one of the line conductors is intentionally tied to ground during installation. So this could be either the positive or negative conductor on the DC side. It could also be on the non-isolated AC side at the inverter. You could very well tie the neutral point or the XO point to ground on the output of that inverter. So that would be your grounded system. Again, one conductor is solidly tied to ground. The ungrounded system is exactly what it sounds like. None of your conductors are intentionally tied to ground. There's a common misconception with the ungrounded system. If I have a ground conductor, therefore it must be a grounded system. And that's actually not the case. On an ungrounded system, you are still going to ground your battery racks, any of your metal equipment, your inverter skid, all of that will still be tied to ground. But the key is all of the line conductors, meaning the positive, negative, and the neutral on the output, all of those are fully isolated from ground. So two similar system types, but they are very different in the way that they are implemented. And that is strictly, is one of my line conductors tied to ground? If yes, I'm on a grounded system. If no, then I am on an ungrounded system. And both are viable for battery energy storage applications.
Seth, what are the dangers of an undetected electrical ground fault, otherwise known as short to ground?
Yeah, that is a very interesting question as well. And it goes back to the answer of the previous question of understanding the difference between a grounded and an ungrounded system. The dangers of an undetected fault will vary depending on which system type that you are operating on. So for example, if I'm on a solidly grounded system, then my dangers are immediate. If I have a short to ground, there will be a significant amount of current pushed from my power source, which is generally going to be your battery or your inverter in these types of systems. They will push as much power as they can through that low ohmic fault to ground because there is a pre-existing return path that exists on the system through the intentional system ground. So a grounded system, the risk is, again, immediate with high leakage currents to ground, which could lead to fires or higher risk of electric shock, also equipment damage and downtime. On an ungrounded system, the danger is less immediate. However, it still is a significant concern. The advantage of the ungrounded system is that you can continue to operate during a first fault situation. And the reason for that is because we are grounding the system during our first fault. So you can either intentionally ground it on a grounded system, or you can leave it ungrounded and let the first fault actually ground your system. The danger on the ungrounded system, while you may not generate high amounts of leakage current and high amounts of dangerous current to ground, what you are risking is if a second fault comes along, you now have a phase-to-phase short through your ground conductor. And that is when explosions happen, when you can easily have fires, all kinds of nasty things can happen along those lines. So while both systems have different danger levels depending on the first fault, they all can lead to disastrous situations if they go undetected or uncleared for a certain period of time.
Seth, can these electrical faults and potential hazardous situations be predicted?
Yes, they can most of the time. This is kind of a double-edged sword question, so to speak. You could, of course, have a ground fault that comes in very quickly, bolts itself to ground. Low ohmic fault, it happens instantaneously. You really can't predict those. You can prevent them with standard maintenance, but those are likely to happen regardless of what you do. What you can predict, however, is intermittent faults and faults that are starting to occur but haven't become a catastrophic issue yet. For example, if you have a high impedance fault or a high ohmic fault, even on a solidly grounded system, that may only generate a few milliamps at most. So the key is being able to trend your data, see changes in the system. So as my insulation begins to deteriorate or as my leakage current values begin to increase, you can then take preventative maintenance actions before a catastrophic incident happens. So this goes back to just data trending and understanding the level of safety on your electrical installation at any given point.
Seth, last question here. What can we do to prevent this all from happening?
Yeah, that's a really great question, and one that I feel quite a bit from the industry. No one wants to have a fire at their installation or a ground fault occur and it go unnoticed and lead to a disastrous incident. There are a lot of things that can be done. The first and the easiest thing is to make sure that the ground fault monitoring scheme that is being used on the system is properly implemented. You want to make sure that you have a system that is giving you reliable information that you can trust, and then you can take corrective action on. So not only do you have to have the proper protection scheme, but you also have to have some type of procedure to tell you what to do when there's a ground fault. You can't just have an alarm or a light go off and say there's a ground fault and expect people to know what to do with that. Oftentimes in the industry, I see these ground fault monitors ignored. They go ignored for days, weeks, months, even years, because nothing catastrophic has happened yet. Well, then the time finally comes where the second ground fault comes in and you now have a catastrophic issue. So some major things you can do are, one, implement a proper ground fault detection and location scheme. You want to isolate your fault to as low a level as you can. Therefore, the technicians on site have all the information they need as to where the fault actually occurred versus trying to find a needle in a haystack in their entire electrical system. The second is training the technicians properly to know what to do when the ground fault monitors go into alarm and tell you that there is an issue. So a proper implementation and proper training can massively mitigate any risks with fires, ground faults, or any really disastrous situations that can occur on your battery energy storage system.
Seth, thank you for joining me here today. A couple key takeaways from the interview. 1, understand your battery energy storage system type. 2, make sure proper ground fault protection scheme is implemented properly. And 3, and lastly, proper action plan if and when a ground fault occurs. Thank you again for joining me here today, and I look forward to connecting with you again in the future.
Yeah, thank you, Justin. I appreciate the opportunity and the questions.